There we go. And God, I need some decent eyes to see what the heck I'm doing. I think it's this one. Nope, I'm wrong. Sorry for the pause. Let's stop that for a second. See, I could have sworn I had the right page open. No. Trust me. Got the wrong page open. Okay, it'll take a few seconds to get into the right one. Gotcha. Okay. Right. And I start again. This time I should be ready for it. Oh God, the writing is so tiny. This one? No. At least I know it's not the right-hand side one. Okay, that's not going to work. The only way I am going to get this to work is by closing every single page and only leaving one page open, which is the one we want. Right. I really am going to have to get a new set of eyes. Yes, I believe we are here. 5.5 inverse trig functions. Is that what you lot are saying?
Yep.
Okay, let's jump and look at some of the situations that we've got here. And we'll start off with the simple ones, which are, how do you find inverse sines of a particular number? For instance, the inverse sine of √3/2. Right, what you need here is you need your unit circle next to you. Because if I now jump back a bit and do this fella, I can kind of show you what's going on. Okay, suppose that was the one you're trying to get. Now that is the same as saying the sine of theta equals √3/2. So somewhere in your unit circle, there is a point who's got a y coordinate equal to √3/2. And it's somewhere here. That guy up there. And when you look at that guy, you find out that the angle there we go. The angle that is the same as that is pi/3. Now, there is a problem with all inverse functions, and that is that they have a domain, and that means that you the answer only comes out as one of the two possible angles. And it's a little bit weird, but this is how it works. When you do the inverse sine, you're only really going to get the angles are going to come out between -pi/2 and pi/2, which is basically the positive ones come from here and your negative answers come from here. If you do an inverse cosine and you look at the answers, the angle that you get, if it's positive, you're going to get it in the first quadrant, and if it's a negative answer, it's going to come out of the second quadrant. And if you do a tangent, an inverse tangent, you're only going to get answers from here and here. So when someone said to you, what's the inverse sine of a particular guy, you go to your unit circle. As I said, there's two of them. Do you know there's another one over here which is also got a y coordinate of root 3 upon 2? The one we're using is this one. We don't use that one because we only pick the answer when it's an inverse sine function. We only have an answer in the first quadrant. So that's where x is coming from. Are you okay with that kind of restriction, that there's two answers you could get, but there's only one that you actually write down? And the one that you write down, if it's in the sine, it's the first and fourth quadrant. If it's an inverse tan, it's also those two quadrants. And if it's an inverse cosine, it's the answer that you'd get in the first or the second quadrant. And that's just a little hiccup that you have to kind of live with. Because to be a function, there can only be one answer to any given value. You're not allowed to have two. Are you okay with that idea?
I'm confused.
Confused, okay. Let's pick an example.
Well, no, I'm just confused. Like when you say like there's only like one answer, do you put like the x coordinate for it, which is 1/2, or would you?
No, you don't. What you do is you put the angle that would generate that point. So, when we were,
last example would be like 60 degrees.
Yeah, but I think they want them in radians, so you would say pi upon 3.
Okay.
Yeah, so the answer to this question is an angle. So if anybody asks you to find the inverse cosine of a half, or the inverse sine of root 3 upon 2, or the inverse tan of a number like 1, the answer you're going to give is the angle they would have, in this case, you're looking for the angle, they would have the sine of that angle equal to that guy. The cosine of this angle is that guy, or the tangent of this angle is that guy. So you're going to be given what angle you would need to make this true. And you can find what angle it is by looking at the unit circle. And it depends on what you've got. If you're looking for an inverse sine of something, right, that guy there, then you only look in the first and fourth quadrants. If you're looking for an inverse cosine equal to something, you only look in the first and second quadrants. And if you're looking for an inverse tangent, you only look in the first and fourth quadrants. And the reason you only look in two of those quadrants is the first quadrant will tell you the answer when these things in here are positive. So if it's inverse sine of a positive fraction, or the inverse cosine, or the inverse tangent of a positive thing, the angle's going to be in the first quadrant, so you look there. And that's the rule of the game. Now, if it's negative, you're going to look in, depending on who you're looking at, one of these three quadrants. So if it's an inverse sine and it's negative, you're going to look for the answer in the fourth quadrant. And if you're looking for the inverse in any of the others, it depends what you're looking for. So it's a little memory thing. You have to know where to look, right? Positive first quadrant, negative one of these quadrants here. Okay.
So if I was looking at the inverse of cosine of.
Okay. So now we're moving on to the fun stuff.
Wait, what? No, I was talking about the second one that you have written down up there.
Oh, this one, the inverse cosine of a half. Yeah.
Yeah. So let me just guess here, or try to figure out. So I'll go to the second quadrant.
Well, is it positive?
Yes.
So where do you look
so
for?
it'd be you'd either be in the first or the fourth, you said.
Yes, but you only look in one of them. So which one of the ones do you look at?
Oh, it would be pi over 3, right? Because
Yes, it's in the first quadrant.
Okay.
So if you're being asked to find the inverse sine of a positive thing, the answer you're going to get is somewhere in the first quadrant. That's it. Don't look for any other answers, even if you can find them, don't use them. And the way the inverse sine, cosine, and tan works is that when it's a positive number here, then the answer will be in the first quadrant. It'll be an angle, and it'll be in the first quadrant. If it is negative, however, then it's a little bit messier, because the quadrant that you get your answer in could be the second or the fourth, depending on what you're wanting. I'll give you an example of a negative one then. If I was trying to find the exact value of the inverse sine of negative root 2 over 2, because it's an inverse sine and it's negative, the rule is the answer you want is in the fourth quadrant. The sine is negative in the fourth quadrant. It's negative in other places, but it's definitely negative in the fourth quadrant, and that's the one we're looking for. So what you would do is you would go to your unit circle, and you'd be looking for an angle theta. So essentially, that's the answer, this angle, that's equal to this fella. Now, when you are looking at a sine, and is it the x or the y coordinate that is negative root 2 over 2?
It's the y.
Right, so you're looking for a y coordinate then, that's negative root 2 over 2, and it's in the fourth quadrant. So that package is going to give you, you're going to look for what angle has a y coordinate of this thing, and it's in the fourth quadrant. So we're looking for a guy down here, and
Oh, so it'd be 7 pi over 4. 350.
right. So you're looking at 7/4 pi, right? Agreed?
Yeah.
Right. Now, nothing wrong with that. But there's another little rule. 7/4 pi is also the same thing as negative 1/4 pi, isn't it?
I don't know.
Yes, it is.
How is that?
Okay, well, let's look at it. If you go all the way around the normal, usual way, which is 7/4 pi, couldn't you move backwards only 1/4 pi and get to the same place?
Oh, okay.
So what that it's telling us is not only do you need to look in the fourth quadrant, the answer that you give is going to be a negative number to indicate that it's a negative inverse sine and that it's in the fourth quadrant. So negative 1/4 is what's going to come out when you're finished. Now 7/4 is the right place, but it's not written in the form that they want the answer to be written. And we're kind of stuck with the rules. This is how it just has to be.
So what if we get an example of that? Because I've seen some examples that it's not exactly the same numbers as the ones in the unit circle. So how do you do that?
Oh, well, how you do them is you use your calculator. So in a lot of ways, it's much easier. So if someone went and said to me, the inverse sine of 0.123, right? Then I just make sure that I'm in radians in my calculator. And I just go inverse sine, which is the second button of my thing. I then type in 0.123, and the answer I get will be an equally horrible answer, 7.065. So in a lot of ways, those questions are easier because you don't actually need to worry about what quadrant it's in, because the calculator will figure it out for you. And you don't need to worry about that the answer's not a nice, pretty answer, because it's not a pretty answer and there's no way it ever will be.
Wait, how did you? I put it in my calculator and it's in radians. What the heck?
Okay, well, I'll check I'm in radians because maybe I made a mistake. Ah, I was in degrees.
It's like,
So-
wait, is my calculator messed up?
Right. Well, the moral of that story. Oh, and I get the answer negative 0.123.
I got positive 0.123.
Oh, for that fella, you're right.
So, I mean, you just put in the inverse of sine, right?
And
Nothing.
then the horrible guy.
Okay. Yeah, that's what I got was 0.123.
Ian, are we okay? Michael, any questions with that?
No questions for me right
Michael, you okay?
now. Yes, can you hear me?
Yes, I can hear you.
Yeah, that was
Yes,
just
I'm okay.
yeah, it was just way easier than I thought it would be.
Okay, well, for the ugly ones, right? It's much
Yeah.
more difficult when the angle is in the unit circle. And so by now you should recognize those questions, because normally when you get the other kind that wants the answer to 2 or 3 decimal places, that's almost always a clue that it's not a unit circle and you're just going to use your calculator. Now, as if we haven't already had enough issues, I'm going to make your life just a little bit harder by showing you a special situation. If you try and find the inverse sign of any number that's bigger than 1 or less than -1, for example, right? The inverse sign of 3. The answer is that it does not exist. Well, let's see how that would make sense. Let's suppose the inverse sine of 3 was equal to some angle theta. Then that's the same thing as saying the sine of theta equals 3. And then I'm going to say, well, I know a lot about the sine function. I've sketched it. And the sine function doesn't only go from 1 to -1. So there's no place in the universe where a single sine of any angle is going to be as big as 3. So if you got a question, and I've seen a couple of homework questions where they gave you that, what's the inverse sine of 2? What's the inverse cosine of 4? Things like that, or -4. And the answer is it doesn't exist.
But you said with this inverse sine of 1, you said that does exist, right?
Yes, that's the last one that works. And the inverse sine of 1 is pi upon 2.
512?
Pi upon 2.
Oh,
Half pi.
okay, gotcha. Oh, the 90-degree, like right
Yes, 90 degree.
Okay, that makes sense.
Now, how about the inverse sine of the cosine of pi upon 3? So this is, I think, the one that it was Ian, I believe, was having issues with. This is
Yeah,
the
that's
kind
me.
of right. That's the kind of combination that's a little bit tricky now, right? Yeah. Okay, here goes. It's really a two-stager. The first thing I'm going to do is I'm going to use my unit circle, and I'm going to find the pi upon 3, which is there, right? And I'm going to find the cosine of pi upon 3. Now, the cosine of pi upon 3 isn't at the x coordinate of this point, which is a half. And now I'm going to find the inverse sine of a half. Right? If you want to, why don't we call it this? We're trying to find an angle theta whose sine is a half. We're trying to find a guy whose y coordinate is equal to a half. And what angle has a y coordinate equal to half? Well, if you go over here, do you see an angle over here on your unit circle that has a y coordinate of a half? What is that angle?
Pi over 6.
So the combined answer to what is the inverse sine of cosine of pi upon 3, the answer is pi upon 6. So first we found the cosine, and then we found the inverse sine of that angle, or that number I should say. And it ends up being the angle pi upon 6. Is that okay?
Yeah, actually.
Okay.
Can you do a tangent one?
Sure. So do you want a tangent? Have you got one handy, or shall I go looking up? Because if I go back,
Yeah, I
that'll
can
be
pull one from the homework right now if you want.
good. Yeah, that would save me because this going in and out's not been too successful with me today.
It's not a compound one though, or whatever. But it's
Whatever's
a
causing you issue, right?
tan inverse of root 3/3.
Okay. So I'm going to call that theta. And so a lot of people find it just easier to see the question in this format because it's more obvious that you're looking for an angle now whose tangent is that. Now, the tangent is the y-coordinate divided by the x-coordinate, and it is in the unit circle. What makes tangents more difficult is that at least when you're finding sines and cosines, don't you just look at an x-coordinate and that's it, or you find the x with the y-coordinate and that is it. When you have to do a tangent, you have to divide the y by the x. So let's see who we've got. This guy here, I've got root 3 upon 2.5. There's a guy here I'm not interested in because I know he doesn't work. And there's another fella up here that looks something like that, right? Now, if I call this guy x and this guy y, right, which happens to be the angle pi upon 3, let's see what happens. The tangent of pi upon 3 is the y-coordinate over the x-coordinate. So far, so good?
Yeah, I think I know what's been screwing me up already.
Oh, well, cool. You fix this thing, and you know it's not that answer then, right? And you try the other one then, and you take the y-coordinate over the other one. That's a 2, by the way, so when you cancel them out, you get root 3. When you cancel this one, you get 1 over root 3. But when you tidy that up, you get the guy you're looking for. So the missing angle is pi upon 6. So when you're doing a tangent, you don't really see the answer. You'll have some choices that look like they might be the answer, and you try it out and it doesn't work. So you try out the other one and hopefully it works the second time. Are we good?
Yeah, I'm good. Thank you.
Right. Let's do another combination one with a tan. Let's do the tangent of the inverse sine of root 2 over 2. So first thing I'm going to do is find out what number is actually an angle that guy is. Well, that's the same thing as saying the sine of theta is root 2 over 2. And if you go to your unit circle, can you trust me on this one, that the angle you get is pi upon 4. Right? Don't know why I'm repeating myself. There we go. It's at pi upon 4. So I now know that that thing there is pi upon 4. So now I'm looking for the tangent of pi upon 4, which is the y-coordinate divided by the x-coordinate. And that ends up being 1. And so the final answer to that question, what is the tan of the inverse sine of root 2 upon 2? The answer to that would be 1. If I put a negative there but kept everything the same, so it would be the tan of the inverse tan of negative root 2 over 2. Suppose I did that. What do you think the final answer would look like?
-1? Because we would be in the fourth quadrant, not in the first.
Yep, nailed it. Now, you see how that giving the fourth quadrant as a negative number actually kind of helps. It might seem a bit awkward, but really in a way it helps. Because your answers will be positive in the first and it'll be negative in the fourth. And that's an easier way to keep track of the sign of your answer. Any other questions about that? Is there any examples you want me to go over? If not, I'll move on to the other section. Okay, this one I will need to zoom around a little bit, so if you can bear with me for a few moments. We're going to be looking at section 5.6, harmonic motion. And it's not that different. Once you get into it, it's not that bad. But I guess at the beginning, it's a bit weird, and that might be part of your issue. So I should be able to share it, and there should only be one of these. Hey, I'm finally getting good at this. Right. Here are some examples of the harmonic ones. So we have y equals 3 sine. In this case, it happens to be called 5t. So what is simple harmonic motion? Harmonic motion, at least when it's simple, involves a sine or a cosine typically, and there will be very often a multiple and another multiple. So it'll be things like 5 cosine 2t and -3 sine 5t, you know, things like that. Now, we are going to find amplitude, we're going to find period. That we've had plenty of practice at. And then we're going to add to the list a thing called frequency. Right. Can you remember that the amplitude, and I better stop sharing for a minute. Right. So can you remember that the amplitude is this number here, and it's always positive, so the amplitude is 3. There's a formula for calculating the period. If we're doing it in radians, which I think we should, it's 2 pi divided by whatever this number is, in this case, 2/5 pi. You're familiar with the number that goes here is going to be the amplitude, the positive value of it, and that the period is a positive number, and it's 2 pi divided by this coefficient. Seems familiar?
Yeah.
Okay. New guy in town, frequency. He's 1 over the period. So the frequency is 5 over 2 pi cycles, if you want its units per second. If you, for example, if you take sound waves, imagine this is a sound wave. Now, if it was that sound wave, what you would hear is a constant tone, right? And if, I'm not musical, but you know, it's like a C+ tone or whatever it would be. The amplitude, which is this distance from here to here, if you were listening to a sound, the amplitude would be basically how loud that tone is. So, you know, if it was like a 3, it'd be a faint kind of hum that you just about catch. And if it was 3,000, your nose would be bleeding, the sound would be that. You know, it's like going at a rock concert and being in next to one of the speakers, right? So the amplitude is a reflection of how strong the sound is, right? How high up and down the thing moves. And when you're looking at you know, the cycles, then 3 is quiet and like 3,000 is really loud. Now, the period is the distance it takes to go from the start to repeat itself. So in this case here, that distance is 2 pi over 5, which is a 1 and a bit. And the frequency represents how many cycles per second. So can you imagine a different sound wave that looks something like this? And that represents 1 second of time. So the frequency, right, would be how many cycles per second. So if I look at this curve, There's 1 cycle, there's 2 cycles, there's 3 cycles, there's 4 cycles. That would be about 4.5 cycles per second. So if you're trying to get your head around what is the frequency is how many times the curve goes up and down and back to its beginning. How many times it does that typically in a second. So if you're into anything to do with waves, frequency is a very common piece of information. Radio waves, you know, if you ever think about it, aren't radio waves given in terms of 1,000 cycles per second, like, you know, 280 hertz? A hertz is just a word for cycles per second. So it's naturally not that hard. It's 1 over the period.
So is this like the amount of revolutions that goes around the unit circle, like per second?
Yeah.
Okay.
If you imagine the sound going around a circle, which is one analogy that we do, if it went and zoomed around the circle 42 times, its frequency would be 42.
Okay.
And yes, question.
I'm sorry. Why? I don't understand how 1 over the 2 pi over 5 turned into 5 over 2 pi.
Oh, it's a little tricky algebra. If you take any fraction, let's say 3/7, and you turn it upside down, it's 7/3. Oh, let's show us a calculation then. 1 on the top over 2/5 pi, right? That's what the calculation would be. That represents 1 on the top divided by 2/5 pi. That can be represented as 1 times the reciprocal.
Oh, okay.
So basically, if you write the period as an improper fraction, which is a good thing to do in these questions, can you see that all you're going to do to get the frequency is invert it, right? Find its reciprocal, turn it upside down.
Okay, yeah.
So
Make sure that I was guessing that it was the reciprocal, but I just want to make sure.
Cool. So calculating it is not that bad then, really, when you think about it. Right, let's look at some more examples of those. So we're back to, hopefully you can see an example here. So we've gone through the amplitude, period, and frequency, and then we're looking at some pictures and we're saying, okay, which one of these 4 pictures best fits 3 sine 5t? Well, I know the period is 2/5, so it could be this shape, right? It could be this shape. I'm kicking out this one because you see that the period here is what, 10 pi, and another one 10 pi, so forget those 2. And now what I'm going to do is, well, if the amplitude's 3, do you see how that goes up to 3 and down to -3? So B would be the correct picture, the first one, this one here. Does that make sense? That the sketch of this should be that.
Yeah, but there's no way to determine frequency?
No, the frequency doesn't involve this. If you wanted to do it, it wouldn't really work well with this. You'd have to imagine how many of these you'd get in a second. And
Okay.
it's just not a useful concept. Let's skip by that one. Skip by that one. Right, let's look at that one. I'm just picking it because the numbers are ugly. You know, decimals and things tend to make life a little bit more awkward. So right now I'm just writing that question down. But it has the same kind of format as the other 3 questions that came before it. Amplitude, period, frequency, and then tell me who the sketch is. So let's see what that looks like. Okay. Anybody, what's the amplitude of this function?
2.5.
Now the period is 2 pi divided by 3.6. Yeah, the answer that they gave, at least the one that was would be expected here, is not a decimal, although it looks like it should be. It looks like you should just go 2 times 3.14 and divide it by 3.6 and get the answer. So I'm going to have to figure out how on earth to get this answer not to be a big horrible decimal, but to be a fraction. So that would be an exact value. So I'm going to stick to 2 pi, and I'm going to think of 3 as 3 6/10. I'm doing this slowly. So it's going to be 2 pi over 3 3/5. That's going to be 2 pi on the top. And if you make this still an improper fraction, you get 18/5. So we've now got 2 pi on the top divided by 18/5, which is 2 pi multiplied by 5/18, which is 10 pi over 18, which eventually becomes 5/9 pi, which I'm going to write like that. So you see, that was quite a long, kind of yucky kind of road to get an answer that's a fraction, even though the way the question started live, it looked much more like a decimal was required. But now that I've got this guy, it's going to make frequency a lot easier. What is the frequency of this particular sinusoidal curve?
Would that just be 9 over 5 pi?
Yes. Reciprocal of period. It's simple as that. The frequency is defined as being 1 over the period. So if you know what the period is and you turn it upside down, that's finding its reciprocal. That's now your frequency. So it's 9/15. You don't need to write the units down. I'm just assuming that it's per second. Those at least 4 questions beginning to make a little bit more sense now.
Yeah.
Yeah.
Okay, so I have a little picture here now to try and match that. I'm looking for a function whose amplitude is 2.5. So that means this picture here, number 2, is no use, and this picture here, number 3, is no use. And I want it to have a period of 5/9. And do you see it's this one here? How do I know it's 5/9? Well, if you look really carefully, do you see the 5/9 there? 5 pi over 9, 5/9.
Yeah.
So it's that one.
I do have a question. Why is it that some of the graphs, when the amplitude, it will give it, like obviously the amplitude is 2.5.
Yeah.
How is it that some of them start on the y coordinate at the 2.5 at the top, and then some start almost looking like it's at the 0?
Well, when it's a sine, it will start at 0 because the sine function begins at 0, 0, and then it takes off. And if it's a cosine function, then when x is 0, it will start at the amplitude, which would be 2.5. So if I went back to this question and I changed that sine to a cosine, right, that's the only thing I did, it would look something like this. I'll try and make my mouse pointer do it. It would start here now, then it would curve down, then it would go like this, then it would curve up, and then it'd finish here.
Okay.
So that's why some of them start at 0 because they're a sine function, and some of them start at a point above the origin, in which case it's because they're a cosine function typically.
Okay. Is it because on the unit circle, sine equals y and cosine equals x? So is it just because it's like reversed kind of?
Yeah, I mean, if you think about the sine and the cosine functions when you go round the unit circle, isn't the sine of 0 got a y coordinate of 0? But the cosine of 0 degrees has a y coordinate of 1. So you can see that in one, the sine function starts at 0, 0, and the cosine function start at 0, 1. So the origin for the sine, and there for the cosine.
Okay. That makes sense. Thank you.
Right, now, they got a couple more like that, and then we hit the next phase. And these fellas here are going to have pretty much everything that you could do to a trig function, a sine and cosine function, is going to get done to it. So I'm going to leave that and go and show you one of mine. Suppose you had y equals 2 the sine of 3x, take away pi. Now we're still going to find amplitude, period, and frequency, and then at the end we're going to sketch it and see how it looks like. The amplitude is 2. The period, if you do it in radians, is 2 pi divided by this guy here. So the period is 2/3 pi. We should be getting much more comfortable with this now. So if the period is 2 pi over 3, what's the frequency of this wave going to be?
Maybe 3 over 2 pi.
Right? We feel more comfortable now about that guy?
Yeah.
And then the last piece of this puzzle is a thing called phase shift. Now, phase shift comes from here, but it also uses that number there. Right. We'll do it in 2 steps. The fact that that is a negative, doesn't that mean that the shape gets shifted to the right? Great?
Yes.
Right. So pi divided by 3. So the phase shift is this fella divided by this fella. And so that's the pi upon 3 thing. So if you were imagining what this function might look like, well, a normal 2 sine would look like this. But if you move everybody to the right pi upon 3, it would look more like the dotted version of itself, right? Exactly the same shape. It'd still go up to 2, down to 2, and it'd still have the same period and so on. But everything gets shifted, in this case, to the right pi upon 3. And that's kind of the last awkward feature that this thing can have.
I have a question about that phase shifting.
Yes.
So when I have a number in the phase shift that I'm able to factor out to find the period, do I still have to multiply the constant times what I factored out?
Okay, let's see if I can recreate what you're talking about. Let's suppose you had a question that looked something like this, right? So
Yeah.
Right. And when it's written in this form, the phase shift is untouched. But when it's not factored, phase shift needs to be divided.
Okay.
So now if you want to, all you need to do is multiply that out, in which case you can use this rule for all of them. But that adds an extra line of working that you probably won't want to do.
Okay.
Are we cool with that?
So for that top example, if you switched the pi with 3x instead of it was like pi minus 3x.
Okay, let's try and draw that.
Would that change anything?
Yes, it would. So we're really getting into weird situations. First thing I'm going to do is that. Right?
Yeah.
Now, what's the formula for doing phase shift? This number divided by that. You see, in this case, the phase shift ends up being a negative pi upon 3.
Okay. Yeah, that makes sense.
So when you're doing any trig function, it should be sine or cosine, whichever it is, a multiple of x, 2x, 3x, negative 5x, followed by some plus or minus, plus pi, plus 7, minus 2 pi, minus a half pi, things like that. That's the kind of the standard format that it should be. As long as you make sure that this is x and that's the number, you can then do this, the number divided by the coefficient of x. What would happen if I did this? What would the amplitude be the same?
Yes.
Correct. Period, would it be the same?
Yes.
Yes. Frequency?
I believe so.
Yes. In fact, everything is yes. Do you know all that plus does to the shape?
Phase shift changes?
No. Phase shift is
Oh.
the same as before. What does that plus 2 at the end do to the normal trig function that you typically would sketch?
It just bumps it up to a vertical shift, right?
Yeah. So I'm not doing this accurately, but can you imagine that's what the first guy looked like? All you do is move them up 2. The amplitude in this case is the measurement that it would have if it was on the x-axis. So it's still 2. And it's still got the same period. And the frequency is 1 over the period, so it's still got the same frequency. And it's still going to be shifted, if it's shifted at all, the same amount. So the phase shift is still the same. So any little plus 2 or minus 7 that they could tag on at the end is not going to change any of the main features. Amplitude, period, frequency, or phase shift don't care about plus 2s at the end or negative 2s at the end. They're the same values either way. And that's kind of all I have time for today. So I will be seeing you tomorrow. And have a look at that CARES grant. A lot of people never apply for things because they always think it's not going to be for them. They're not going to get it. The number of times I've seen people who actually apply thinking they wouldn't get it, and then they end up getting it is surprisingly common. I mean, so think seriously about it. I don't think it would take you that long to fill it out. The way I see it is all they can say is no, and they probably won't even say no. All they will say is nothing, and you won't get a reply back. So, you know, what's 10 minutes out of your life, and you may get $1,000 for it. So look into that seriously, and at least give it a shot. Now, if you're really a millionaire, I guess you don't need to, but if you were a millionaire, I don't know, you might still come to college, but probably not. Okay, have a nice day, everybody. I shall see you tomorrow. Bye-bye.